Hi, this is Tzvi Rosen. In today's lecture, we'll be talking about Noetherian rings. We'll start by talking about various operations on rings that preserve the Noetherian condition. Then we'll state and prove Hilbert Basis Theorem. And finally, we'll show that in Noetherian rings, all ideals have primary decompositions. Okay, let's get started. First, we'll recall the definition of Noetherian, and we'll state three equivalent conditions for being Noetherian. So first, we have the ascending chain condition on ideals. Which states that if you have an ascending chain, I1 contained in I2, contained in I3, etc., then this sequence of ideals is stationary. In other words, it's eventually constant, like all of the subsequent ideals are equal to some fixed ideal in the chain. Okay, the second condition, which is equivalent to the first, is called the maximal condition. On ideals, that any collection of ideals has a maximal element. Of ideals in the ring has a maximal element. And finally, since we proved that any Noetherian module, or a module is Noetherian if and only if all of its submodules are finitely generated. In this case, the submodules are the ideals, so this is the condition that all ideals are finitely generated. Okay, so these three equivalent conditions, characterize a Noetherian ring. Okay. So now that we have our definition of Etherean, we can talk about various operations preserving that property. First is homomorphism. So if you have an Etherean ring, and we have a homomorphism of rings, phi from A to B, surjective homomorphism of rings, then B is also an Etherean ring. Okay, and this is not hard to prove. Because you have a surjective homomorphism of rings, B is isomorphic to A modulo some ideal, which is the kernel of the homomorphism. And we know that when you have a quotient of A by an ideal, the ideals of the quotient are in bijection with the ideals of A containing the ideal A. So ideals of B are in order-preserving bijection, let's say. With ideals of A containing A. So that means that, for instance, any collection of ideals in B corresponds to a collection of ideals in A. which has a maximal element, and by the same token, that collection has a maximal element in B. So since A satisfies maximal condition, okay, so does B. Okay, so that proves that the image of a homomorphism of an Etherean ring is also an Etherean. Okay, now we'll look at finitely generated modules of an Etherean rings. If you have A contained in B, where B is also a ring, A is an Etherean ring, and B is finitely generated as an A module, then B is an Etherean ring. Okay? Let's prove this. So since B is finitely generated A module, it is Noetherian as an A module. Okay, so B finitely generated A module implies Noetherian as an A module. Okay, and we proved this in the last chapter using exact sequences. But then how do you get from being Noetherian as an A module to being Noetherian as a B module? Well, if I'm, for instance, Noetherian as an A module, then any A submodule of B is finitely generated. But any B submodule of B is also an A submodule of B. Okay, so since every B submodule, okay, and when we say A submodule or B submodule, we're talking about subgroups that are preserved under multiplication by elements of A or B, respectively. So since every B submodule is an A submodule, since if I'm preserved by multiplication by B, I'm certainly closed under multiplication by A. These are finitely generated, implying that B is Noetherian as a B module, which means it's an Etherean ring. Okay. Localization. So if we have A, an Etherean ring, and we have S in A multiplicatively closed subset, then S inverse A, the localization of A at S, is also Noetherian. Okay, and the proof of this is similar to the proof in the case of the quotient. So the proof the ideals of S inverse A are in order-preserving bijection. With the ideals of A not meeting S. So, given that we have this bijection, if we have some collection of ideals in the localization, those are in bijection with ideals in the original ring, which therefore have a maximal element. Mapping that forward, using the same bijection, you have a maximal element in the localization. So A satisfies maximal condition, implies S inverse A has the maximal condition as well. Okay, And an alternative proof is also offered in Atiya McDonald, which uses the finite generation of ideals. So alternatively, so let's say you have an ideal little a in A, then when you map forward to the localization, so the corresponding ideal there will be generated by, so we know that this is going to be generated by some collection of elements of the ring, finite collection. And so this ideal will be generated by x1 over 1 through xn over 1. So you also have finite generation of ideals in the localization. So A has finite generation of ideals implies the localization does. Okay. And that brings us to the Hilbert Basis Theorem. And this is a major result about Noetherian rings, proved by David Hilbert, seen here with a nice hat. And it goes as follows. Let A be a Noetherian ring then A adjoin X is also Noetherian. Okay, and this has major consequences. For instance, this would mean that any finitely generated polynomial ring or any finitely generated algebra will be a Noetherian ring, a finitely generated algebra over a Noetherian ring. Okay, so let's prove this. The idea is as follows. So when we're going to prove that ideals will be finitely generated. So take any ideal A in A in A adjoin X. Okay, we want to show that this is finitely generated. So the first observation we want to make is that we can define the leading term or the initial term in of f to be the coefficient of the highest power of x in f. Okay? And it's not hard to see that the set in of f for f in A is an ideal in A. Okay? Because, so you could take initial terms. So let's go ahead and prove it. Why not? So if you have, let's say I have, let's call this in A. So if you have B and C in A, that means that that there's some polynomial FB, which is equal to B x to the r plus lower order terms, and there's some FC equals C x to the s plus lower order terms, both of these in the ideal. Okay. And now, without loss of generality, you can assume that R is greater than S, greater than or equal to S. So then you can take FB plus x to the r minus s fc, okay, this is in the ideal A, and this has initial term b plus c. So this means that, sorry, this should say in A implies b plus c is in A. Okay, and scaling, you can easily scale any polynomial which scales the initial term. So clearly this is an ideal. So now that we have that initial ideal of A is an ideal of A, this implies that it's finitely generated by the Noetherian condition. So initial ideal of A is finitely generated. And in particular, we can say that it's equal to some collection to the ideal generated by A1 through AN. Okay. And since these are in the initial ideal, that means that they are actually the leading coefficients for some polynomials in our ideal A. So that means that there exists f1 through fn such that fi is equal to ai x to the ri plus lower order terms. Okay. Well, let's think about this collection of polynomials. There's going to be, because it's finitely many polynomials, that means that there's going to be some highest degree. Max Ri equals, let's call it m, will be finite. Now, given G and A, I'm going to make the claim that G is equal to some polynomial f, which is in the which is generated by the fi's, and some polynomial G tilde, which has degree less than m. So where f is in the ideal generated by f1 through fm, and G tilde and degree of G tilde is less than m. Okay. So if G has degree less than m, then we're done. So if degree G is less than m, we are done. So assume or suppose G has degree higher than m, or at least m. Greater than or equal to m. Then we can write G equals a x to the k, where k is plus lower order terms, where k is at least m. And we know that A will be equal to some A linear combination of the AIs. So we have Ci AI, I equals 1 to n, where Ci, these are arbitrary elements of A. Well, that means that I can take the following polynomial, f equals the sum of Ci x to the k minus ri fi. Okay, and recall that fi has leading term ai x to the ri. Okay, now this will have leading, and add in the indices here, this has leading term ax to the k. So I can take, I can now show that g equals f plus g tilde, where degree of g tilde is strictly smaller. Sorry, I should make this actually, yeah, where degree of g tilde is strictly smaller than the degree of g, right? Because this f already includes the leading term. So repeating this inductively, I can then obtain a g tilde which has degree smaller than m. So g tilde will have degree smaller than m. Okay. So what we've proved is that the ideal A can really be thought of as the ideal generated by these f1 through fn, which we got from the initial ideal, combined with some finitely generated module. So it'll be the intersection of A with M, where M is basically the ideal generated, the A module generated by 1x x squared up through xm minus 1. Okay. So in particular, so this is as an A module. In particular, A intersect M, now it's a finitely generated A module. And we know that a finitely generated module over an Etherean ring is Noetherian. Okay, so it's Noetherian as an A module. Okay, but then it's also Noetherian as an A adjoint X module. Okay. And in particular, it will be finitely generated. Finitely generated by, let's give it G1 through GK. And what that means for us is that A, as an ideal of A adjoint X, is generated by the F's and the G's. Okay, so using that, so making no assumptions other than that the coefficient ring is Noetherian, we now have that this ideal is finitely generated. Okay, so A is finitely generated, which means that A adjoint X is Noetherian. Okay, and that proves Hilbert's basis theorem. Okay. So quick corollary of that is that finitely generated algebras over Noetherian rings are also going to be Noetherian, right? Because, so A adjoint X, Noetherian, we'll then apply that inductively. Okay, so the induction argument would tell us that A adjoint X1 through Xn is also Noetherian. And as we saw before, homomorphisms of the image of homomorphisms of Noetherian rings are also Noetherian, so that implies that A adjoint X1 up to Xn, even quotiented by some ideal, is also Noetherian. So Hilbert's basis theorem gives us quite a lot. Okay. Now we'll address we'll address primary decomposition in Noetherian rings. We saw when we spoke about primary decompositions originally, we proved quite a lot about them, but we also saw that there are examples of ideals that do not have primary decomposition. But in an Etherean ring, every ideal has a primary decomposition. Okay, and we can prove this over the course of two lemmas. So the first lemma regards irreducible decomposition. So we say that an ideal is irreducible. So ideal A in A is irreducible if, given the equation A equals B intersect C, then either A equals B or A equals C. Okay, so there's no, you can't kind of pull A apart as the intersection of two strictly bigger things. It can only be expressed as its own thing. Okay, obviously B and C ideals. Now we state the lemma. Okay, let A be an Etherean ring. Then every ideal A in A can be written as a finite intersection, or as an intersection of finitely many irreducible ideals. Okay, and this is called an irreducible decomposition. Okay, let's prove this. We'll argue by way of contradiction, so suppose not. So that means we have a non-empty set of ideals that can't be written this way, which means that that collection of ideals has to have a maximal element by the Noetherian maximal condition. So the fact that A is Noetherian implies that the set of ideals without irreducible decomposition must have a maximal element. Okay. Consider an ideal A of this type, maximal in this way. Okay. A can't be irreducible, because if it were irreducible, then it would be written as a finite intersection of just itself. So A is not irreducible. So that means we have A equal to B intersect C with B strictly greater, so not B or containing A strictly, and C containing A strictly. Okay. But so both of these are larger than A, and because A was maximal in the set of ideals without irreducible decomposition, that means that B and C must have irreducible decomposition. Okay, but then A can be written as, so that means that they both can be written as a finite sum, as a finite intersection of irreducibles, but then A can just be written as a finite intersection of those. And that gives us our contradiction. Okay, and so that proves that every ideal must have this irreducible decomposition. Now we would like to show that these irreducible ideals are actually primary, which would mean that we now have a primary decomposition for every ideal. So let's prove this. So we'll take A in A, an irreducible ideal. Okay. So plainly, A is primary in A if and only if 0 is primary in the ideal A mod A. Okay, and you can check that the conditions line up perfectly. So it's enough to show that if the zero ideal is irreducible, then it's primary. Okay, so the 0 ideal is irreducible, then it's also primary. Okay, so let's take, we're assuming 0 is irreducible. We want to prove that it's primary. So we'll take xy in 0, and we're going to try and show that either y is equal to 0 or x to the n is equal to 0 for some n. Okay. Well, okay, if y equals 0, we're done. So we can assume that y is not equal to 0. Okay. Then we'll consider the following chain of ideals. So we'll take the annihilator of x. Okay, these are the elements of A that when you multiply by x, you get 0. That's contained in the annihilator of x squared, which is contained in the annihilator of x cubed, etc. So this is an ascending chain. Okay, and since we're working in an Etherean ring, okay, so probably should have stated that at the outset. A is an Etherean ring for which irreducibles are primary. So we're considering this ascending chain. So this is going to be stationary. So we'll have some n such that the annihilator of x to the n is equal to all subsequent annihilators, x to the n plus 1, etc. We claim that the intersection of x to the n and the ideal y is going to be the 0 ideal. Okay? If not, we would have some non-zero element. Okay, so suppose not. Then there is A not equal to 0 with A in both ideals. Okay. By virtue of being in the ideal generated by y, A is equal to by, but that means that Ax is going to be equal to 0, right? Because xy is 0. On the other hand, the fact that A is in the ideal x to the n that means that A can be written as cx to the n, which in turn means that since Ax equals 0, that means that cx to the n plus 1 equals 0. Okay, just by plugging in, just by plugging A into the previous equation. But that means that c is in the annihilator of x to the n plus 1, which, by what we observed on the last page, tells us that c is in the annihilator of x to the n. But if c is in the annihilator of x to the n, then this equation tells us that A is equal to 0. Okay? So that tells us that this intersection of x to the n and y is equal to 0. But if 0 is irreducible, then we know that one of the components of that intersection must be equal to itself, to 0. And since we know y is not equal to 0, that means that x to the n must be equal to 0. So that allows us to conclude that 0 is primary. Okay? And in turn, that implies that any ideal which is irreducible in an Etherean ring is primary. Okay, so putting those two lemmas together, we now have that if A is an Etherean ring, since we can take, so for any ideal A and A, we can construct its irreducible decomposition. Since all of those ideals are primary, this has a primary decomposition. Okay, and there are additional nice features of this primary decomposition related to its associated primes that you only get in an Etherean ring. But I'll leave you to check Atiya McDonald for those details, and we'll conclude with this. Thank you.